Okay, so after the approximate ITM, the next methods, which are Box-Mahler and Marsalia's polar method. For this we need tools from analysis too. So here's a small recap. So the first tool we need is a C1 diffeomorphism. A C1 diffeomorphism is a map phi from U to V. U and V are open subsets of N. This phi has to be bijective, and phi as well as its inverse have to be continuously differentiable. Well, phi is continuously differentiable, so the derivative exists. And well, we have this Jacobi matrix as a representation with respect to the canonical basis of Rn. So phi is a map from Rn to Rn, or subsets of Rn to Rn. So we have n components, phi n up to phi 1 up to phi n. And we have also n variables, and delta 1, delta 2, delta n are then the partial derivative with respect to the first, the second, or the nth component. So for C1 diffeomorphism, well, we can write down the Jacobi matrix, and the Jacobi matrix is given as this here. Okay, why these two tools are helpful? These two definitions. Well, we have this change of variables for integrals theorem or rule, whatever you like to call it. So phi is a C1 diffeomorphism, and we want to try to integrate our function f. F goes from V to R. So we want to try to integrate this over V. This might be difficult, so we might try to change coordinates using this function phi here. And then the theorem tells you, the change of variables for integral theorem tells you that instead of integrating f over v, we can try to integrate this expression here over u, and we have equality. And what are we having here? Here we have the composition of f and phi, and here we multiply everything with the determinant of the Jacobi matrix of our transformation phi, and then we have equality of the integrals. The expression on the right hand side looks a bit more difficult at first, but it really helps to simplify things. And before we go on to Box-Mahler or Marsalia's polar method, I want to give you a nice illustration of this. And this illustration is polar coordinates, which is one of the classical transformation from R2. So polar coordinates map 0 infinity, 0 to pi, open to R2. And what we are doing, so we have two components, T1 and T2. So we map R and phi to R cosine phi, R sine phi. So instead of considering a point in R2 by its classical coordinates, R is the length of the point considered as a vector, and phi is the angle of this point. The angle, not angel, angle of this point. R is radius, phi is the angle, and so we get our point in R2 here. So what are the partial derivatives? So we can differentiate T1 with respect to R and with respect to phi. Differentiating with respect to R, just the R disappears. Differentiating the cosine gives us minus sine. And the same we have for the second component, T2. Differentiating with respect to R, only the R in front of the sine disappears. And differentiating sine gives us cosine. So here we have R cosine phi, and we can collect this in the Jacobi matrix. Here we have cosine phi minus R sine phi, R cosine phi. So this is our Jacobi matrix, and in the next step we can compute the determinant of this 2 times 2 matrix. This is cosine phi times R cosine phi plus, minus sine phi times minus R sine phi. So we have an R in each expression, and behind the R we have cosine squared plus sine squared, and cosine squared plus sine squared is 1, so only the R survives here. Okay, so we have this map, which is a C1 diffeomorphism. If you if you play around a bit with the sets, because this openness is in the definition. But for applying it to integrals later on, we will see we can ignore lower dimensional subsets. This is a Jacobi matrix, and this is the determinant of the Jacobi matrix. Okay, so as I said, changes of the integrand and lower dimensional subsets do not influence the integral. So one can be a bit sloppy about openness or closeness of the set U. So here's an application, an example, an application. So we want to compute the area of the unit circle. I denoted this by V overline. So V overline is a closed unit circle in R2. And we want to reduce it by computing an integral over overline U, and overline U is the compact interval 0, 1 times the compact interval 0, 2 pi, which has a simpler structure. And then this polar coordinates map, if we apply T to overline U, then we get overline V. So T maps overline U on overline V, and T respected to the inner points of our sets is a C1 diffeomorphism. And since lower dimensional subsets do not influence the integrals, so we can work with this. Okay, why we are doing this? So the Lebesgue measure, the two-dimensional Lebesgue measure of overline V, that's exactly the area of our circle. And writing down this a bit more complicated, so we can write this as an integral over the constant 1 function of the constant 1 function over overline V with respect to the Lebesgue measure. And well, we have our change of variables formula. So we can now use T for the change of the variables. So instead of integrating over overline V, we can integrate over overline U. And here would be the composition of F and T, but F is 1, so here's 1 and we don't see it. And here we have the absolute value of the Jacobi determinant, which we have computed, and here we integrate still with respect to the two-dimensional Lebesgue measure. Okay, this Jacobi determinant is R. So U is 0 times 0 until 2 pi and 0, 1. So it's a product of this. So we integrate R with respect to phi from 0 to 2 pi, and with respect to R to 0, 1. And if you do this by some elementary computations, we're just getting pi. So in this way you can analytically compute the value, can prove that the area of the unit circle is pi. I didn't do this example because pi is very fancy, but to introduce polar coordinates and for a recap of this method, because polar coordinates we will need crucially in the following.